All right, so we're going to continue looking at vectors today. So we got sort of an introduction on Friday. Today we're going to see more of the connection of how these vectors, how it relates to trigonometry. So we'll be connecting this to some sine and cosine today. We're going to start by looking at unit vectors. So we're going to fill in. A unit vector has a magnitude of 1. Remember, magnitude is another term for length. If you think about the unit circle, it has a radius of 1. So a unit vector is a length of 1. So we're going to start by finding the unit vector in the same direction as this vector v, 4i minus 3j. Now, just by looking at this, if we were to do our magnitude formula right away, we can see that it's not a unit vector to start off with. If we find our length, we get the square root of 16 plus 9, which is the square root of 25. So the original length is actually 5. And if we were to graph this vector on our axes, it would look something like this. It's got a positive I component, a negative j component. So imagine that this original length here is 5. We're going to cut this down. We're going to break it into a smaller piece. So we're only looking at 1/5 of that length so that it now has a length of 1. But we still want it to go in the same direction. So we have this formula that we're going to use over here to find a unit vector. We're going to take each component of the original vector, divide it by the original length of 5, and that's going to get us down to this length of 1. All right, the magnitude of vector v, we already found that over here, so let's go ahead and label this. What we originally wrote, we can label that with our symbol for magnitude. So we know that's going to be 5. And then we're going to split this up. So we want to divide each piece by 5, giving us 4/5 I minus 3/5 j. Now we can check to see that this new vector is a unit vector by finding its magnitude. Use the magnitude formula, make sure that it's equal to 1. So when we put this one in, we have 4/5 squared plus negative 3/5 squared. When we square a fraction, we can square the numerator, square the denominator, so we get 16/25 plus 9/25. Add our numerator, keep our denominator the same, so we get 25/25, which is 1. What's the not absolute value, what's the square root of 1? Great, so we know that it is in fact a unit vector. All right, one thing we talked about on Friday, sort of the definition of a vector, is that it's a quantity that has both a magnitude and a direction. So I gave you an example on Friday. Imagine the situation if I'm walking toward the classroom door. One type of magnitude could be a velocity. So my magnitude, maybe I'm walking at a velocity of 6 kilometers per hour, and my direction is toward the door. We're going to look at a more formal method for writing a vector in terms of its magnitude and direction. So imagine that we have this ij vector. Since it's an ij vector, it starts at 0, 0. So let's label this as our starting point. And on this blank axis, let's draw a vector out here. We'll say this is vector v that's equal to ai plus bj. In the x direction, if we make a tick mark down here, this is going to be our a distance. In the j direction, making a mark off to the side, this is our b distance. Now we're going to turn this vector into a right triangle. So we're going to draw a vertical line straight down to the x-axis. We can label the sides of our triangle. So the base length, of course, is a. The height of our triangle is b. We can label the hypotenuse of our triangle, which is the actual vector. That's the magnitude of this vector. It's the length. So let's use the magnitude symbol for our hypotenuse. The final thing that we're going to label in this picture is a little angle theta. In these situations, theta will always be measured up from the positive x-axis, just like what we normally do with theta in a diagram like this. All right, so now we're going to connect this to SOHCAHTOA. We have a right triangle, and so we can use our SOHCAHTOA definitions to write some relationships amongst our sides. We can start by saying that cosine of theta, we know that cosine is the adjacent over the hypotenuse. The adjacent side length is A, and our hypotenuse is the magnitude of V. Right below, let's write a similar equation for sine. What would be the sine ratio? Go ahead, Chandler. Perfect. All right, now our original vector v is based on a and b. We now have a and b in these new equations. We're going to solve for a and b by multiplying both sides by the magnitude. So we get two new versions of these equations. So we have the magnitude of vector v times cosine theta represents a. Magnitude of v sine theta is b. All right, now replacing these for a and b, back up here, we have a new way to define a vector. So instead of writing ai, we can write magnitude of vector v cosine theta I. And then in place of b, magnitude of vector v sine theta. So this is how we do our vector in terms of its magnitude and its direction. Up in front, we have our magnitude, and the direction is defined by the angle. Oh yeah, thanks. Not B, should be J. All right, so now we're going to apply this. So we're going to look at a basic example of writing a vector in terms of its magnitude and direction. So they've told us that our magnitude is 10, our direction angle is 60 degrees. So using that formula that we did above, we're going to write 10 cosine 60 degrees I plus 10 sine 60 degrees J. Now we're going to simplify these down. If it's an angle that's easy enough to do on the unit circle, you can use the unit circle value. You can also type this into your calculator. Thinking about the unit circle, cosine 60 degrees is 1/2, and sine 60 degrees is √3/2. All right, so we can write this as 5i plus 5√3j. You could also have typed this into your calculator. Make sure that your calculator is in degree mode. We'll get the same answer. We'll get the same answer for the first one. 10 cosine 60 should just be 5. When we do 10 sine 60, we're going to get a decimal approximation that's representing 5 square root 3. So it's about 8.7. All right, so thinking about that same thing, let's take a look at our next problem. So this time we have a velocity vector representing the direction and speed of an object in motion. Suppose that the wind is blowing at, this is a typo here, the wind is blowing at 60 miles per hour in the direction north 40 degrees east. We're going to express its velocity as a vector in terms of I and j. You can think about this when you're walking to the parking lot at the end of the day and it's super windy, because I heard on the news that we're supposed to have a lot of wind this afternoon. Bring in the storm in. All right, we have a bearing given to us to help us just describe our direction angle. We're going to start by drawing a sketch. Since it is north 40 degrees east, we're going to start at 0, 0. We're going to travel north first, and then would east be to the right or to the left? Did you say to the right? Okay. I always think about the map of the U.S. and I think about the East Coast and the West Coast. That helps me. All right, so north 40 degrees east. So the thing about a bearing is that the angle that they've given us, it's not actually the angle theta that we want. It's the angle that's measured from the north-south line. And so we want to make sure that we're careful in how we're labeling our diagram. So if that's 40 degrees and our angle theta is always measured from the positive x-axis, what is theta? Is 50. So we're just going to subtract that from 90. All right, we have our magnitude. Our magnitude is our velocity, in this case 60. So our magnitude is 60. We have our direction angle of 50 degrees. So we're going to plug these pieces into our formula. So we have our magnitude times cosine theta I plus 60 sine 50 degrees j. Now this one we have to type into our calculator. So 50 degrees is not a perfect angle that's on our unit circle. So let's go ahead and type these in. So we have 60 cosine 50 and 60 sine 50. All right, so if we do a little bit of rounding here, let's actually round these up to the nearest whole number. We have about 39i plus 46j. Yep, CJ. I will tell you rounding information on the test, definitely. All right, what else, Matt? Okay, awesome. All right, we have one last problem we're going to look at. Let's turn over to the back side. All right, so we've talked a little bit about velocity vectors. Velocity is one application of a magnitude. Another common vector is a force vector, represents a push or pull of some type. And force vectors are happening all the time, all around us. So suppose that you are holding a 10-pound box. If you sort of look at this diagram here off to the side, there are two forces that would be acting on this box. We can call force 1 the force that gravity is exerting. So gravity exerts a force of 10 pounds downwards. So notice how there's a direction that's being shown. Force 1 is an example of a vector. Force 2 would be the force that you are exerting to hold up this box. So you're exerting a force of 10 pounds upwards. When we have more than one force acting on an object, we get a resultant force. It's the sum of adding those forces together. So in this case, we only have two forces that we're looking at. So force 1 plus force 2 would be our resultant force. In this situation, the object is not moving. The forces cancel each other out, so our resultant force is equal to 0. This isn't always the case. So in our last problem, suppose that there are two forces, like we did before, we'll call them force 1 and force 2, of magnitudes 30 and 60 pounds respectively. So force 1 is a magnitude of 30 pounds, force 2 is a magnitude of 60. These forces are acting on an object. The direction of force 1 is north 10 degrees east, direction of force 2 is north 60 degrees east. We're going to find the magnitude and direction angle of the resultant force. All right, first we're going to start by drawing a picture. We're going to use the bearing information to help us see kind of what these forces look like. Both of these forces, or both of these bearings, are northeast. And so all of this is going to be happening in the first quadrant. If you think about starting down here and we go northeast, we're going to end up somewhere in there. So let's draw our first force. We're going north 10 degrees east. 10 degrees will just be a kind of a little tiny angle that we'll label right here, and let's label this as force 1. And then force 2 is north 60 degrees east. So this one is going to go a little bit further out. And we'll label that 60 degrees. There we go. All right, so let's talk about the direction angle theta that we would use for each force. What would be our value of theta for force 1? All right, great, 80 degrees. So we're going to subtract that little 10 degrees from 90. What's the value of our direction angle for force 2? Great. All right, so we're going to start by writing an ij vector to represent these forces separately. So we're going to use what we did on the front side of writing our vector in terms of its magnitude and direction. We already know the direction in terms of an angle theta. The magnitude would be the amount of force, the amount of pounds that are acting on that force. And so force 1 has a magnitude of 30. So our ij vector for force 1 is going to be 30 cosine 80 degrees I plus 30 sine 80 degrees J. All right, we're going to put these into our calculator. If you type these in, we should get 5.2I plus 29.5J. All right, now we're going to do the same thing for force 2. So we have a different angle. This time our angle will be 30 degrees. We also have a different magnitude. So the magnitude acting on force 2 is 60 pounds. All right, 30 degrees is on the unit circle, so you could use that method, or we can type these into our calculator. So we should end up getting 52I plus 30J. All right, so now we're going to find our resultant force, which is F1 plus F2. We're going to write it as in terms of an ij vector. So we're going to add the I components together, 5.2 plus 52, so that will be in front of I. And in front of the j, we have 29.5 plus 30. So altogether we have 57.2i plus 59.5j. All right, so let's pause here and take a look at what this question is asking us. It wants us to find two things about the resultant force. It wants us to find the magnitude and the direction. Once we have the resultant force in terms of an ij vector, it's easy to find the magnitude of this. We're just going to plug these values in for A and B into that magnitude formula. So altogether we should end up getting 82.5. Since this is the magnitude and it's representing a force vector, we're going to use the units of pounds. So this is part of our answer. That's the magnitude of our resultant force. All right, now we need to get the direction angle of the resultant force. This one is a little bit harder. We're going to make another sketch showing what's really going on when we add these two forces together. Let's draw force 1 again, which would look something like this. We're going to label that F1. Now, remember we talked on Friday about how to geometrically add vectors. So if we wanted to add F1 plus F2, imagine that we're going to take F2, pull it off of the paper. We're going to have the start of F2. It's going to start at the end of F1. So we're just going to move it upwards. We can show that on this new picture. F2 is at a little bit of a different slope. So it would maybe look something like this. Pick it up, put it onto the end of F1. Now we're going to draw a new vector from 0, 0. Let's see if I can make that a little straighter. Going all the way to the end of F2. And this new vector geometrically represents the addition of doing F1 plus F2. So to find the direction angle of this resultant force, F1 plus F2, we're trying to find this angle theta right here, the angle theta that would go to this red line. If we make one big right triangle out of F1, F2, we have some information about the lengths of this triangle. The value in front of I of our resultant force, that represents the length in the A direction. The I direction across the x-axis is 57.2. Over here, this is our B value. So that's going to give us the height, 59.5. All right. So if we think about this right triangle, we have the opposite side and we have the adjacent side. If we think about SOHCAHTOA, which one of our trig functions would help us to find our angle that has something to do with the opposite and the adjacent? We're going to use tangent. This is very similar to what we did with our complex numbers. Tan theta is B over A. And so theta would be the tan inverse of B over A. All of this should look familiar. We're just applying it in a slightly different context. Now let's plug in our values for B and A. So let's label over here B was the 59.5 and A was 57.2. All right, this is our direction angle. So let's round this to the nearest whole degree. So let's round it down to 46 degrees. We know the answer on the calculator will match our real answer that we want because our angle's in the first quadrant. This is a first quadrant angle. Now, one thing I have to tell you, there is one problem in the homework assignment where the bearing that's given to you is a southeast bearing, and so you'll end up with a direction angle that's actually in the fourth quadrant. So just remember that the answer your calculator gives, if it gives you a negative angle, like negative 46, that's down in the fourth quadrant, we'll turn it into a positive angle by adding 360 onto the end. Okay, so just one final thing with this. So this was a situation involving the resultant force of a force vector. We also talked about velocity vectors, and so an application of this, if you were doing something like, imagine a plane that's flying in the air, and there's the speed of the plane in still air, and then maybe it's flying with a tailwind, and so the speed of the wind is kind of helping it along, helping that plane to go a little bit faster. We could say something like vector v is the velocity of the plane in still air. We can say that w is the velocity of the wind. And so if you found the resultant force by adding v plus w, you would get the actual speed and direction of the plane in terms of, related to the ground. So that's kind of another connection of how it would work if we were using velocity for our magnitude instead.